Alright, last day for the unit, continuing on with section 12.5. We're going to talk about complex conjugates. Again, something we've done before. This isn't new. This is just going to be real simple and fun. So we want to look at the relationship between complex numbers and their conjugates, both in standard form and in trig form. So first, a little bit of review. The complex conjugate. So if I have some complex number z equals a plus bi, then its conjugate is a minus bi. This notation, z with the bar over the top, that stands for conjugate. So that's a notation for conjugate. So I want you to pause the video in a second. So take a minute and multiply a complex number and its conjugate, and divide a complex number and its conjugate, and look at what these should come out to be. The multiplication you should already know, actually, because we do that a lot. The division, not as much, but it should still make sense. So pause the video, multiply conjugates together, divide conjugates, simplify, and then we'll discuss. Okay, so we should know or remember that when we multiply a complex number by its conjugate, what happens is the imaginary part goes away. And so in this case, what we're left with is a squared plus b squared. So it's just going to be some real number, and we have no imaginary component to the complex number anymore. We should know that because that is part of what we have to do when we have division of complex numbers, is we always multiply by the conjugate to get the imaginary part out of the denominator. So when we actually divide a number by its conjugate, by its complex conjugate, we need to multiply the numerator and denominator by the conjugate. So we multiply the numerator and denominator by a plus bi over a plus bi. The numerator becomes a squared plus 2abi plus b squared I squared. I squared is negative 1 over a squared plus b squared, which we already knew from the previous part. So then if we rewrite this in standard form, we end up with a squared minus b squared over a squared plus b squared plus 2ab over a squared plus b squared I. So it's not overly complicated, at least the algebra is not, but the answer doesn't look very nice. So now let's look at doing this stuff but in trig form. So we know if we have some complex number z equals a plus bi, then in trig form this is z equals r times cosine of theta plus I sine of theta, or we can write it as r cis of theta. So with that in mind, I want you to try and think about or figure out what is its conjugate in trig form. So pause the video. There's a few ways in which you could come up with this, but try to figure it out. Unpause when you're ready to check your work. Okay, so depending on your creativity, your remembrance of even and odd identities for trig, and your simplification, you may or may not have come up with that the complex conjugate of a complex number in trig form is r cis of negative theta. So how do we come up with that? Well, first we know that the the conjugate is going to be the same number but with an opposite middle term. So instead of plus I sine theta, I make it minus I sine theta. Okay, well, with my trig properties, I know that I can take since this is sine, I can take this minus and make it a plus and make this negative theta, because my trig identity, or my even odd identity, tells me that that negative sine of theta equals sine of negative theta. So that's one of my trig identities. So I make this negative theta. Now, I want the thetas to match, so because of my even and odd identity for cosine, I know cosine of theta equals cosine of negative theta. So I make this cosine of negative theta instead of cosine of theta. Now that the thetas are the same, I can rewrite this recognizing that the conjugate is RCIS of negative theta. Okay, so we should have a bar over it. We know that we have a complex number z equals RCIS of theta, z bar equals RCIS of negative theta. Now again, sticking with trig form, I want you to find the product of the conjugates and the quotient of the conjugates. Pause the video, unpause when you are ready to check your work. Okay, so using our properties of multiplication of complex numbers in trig form, I know that if I have z times z bar, it's going to be r squared CIS of theta plus negative theta. Theta plus negative theta is 0, so I end up with r squared CIS of 0. That should make sense because we know that the imaginary part goes away when we multiply the complex conjugates. So in this case, if I was to write this out in long form of trig form of a complex number, the sign term with the imaginary component would go to 0. With the division, I use my properties of dividing complex numbers in trig form again. So I actually divide the r value, so r over r, and I subtract the thetas. So I do theta minus negative theta, which ends up being theta plus theta. So I end up with 1 CIS of 2 theta, or just CIS of 2 theta. So the point of looking at this is seeing how when we are in trig form, not only are the operations very simple, multiplication and division, but the results are also very clean and nice, as opposed to, back here, for the division especially, the results was kind of messy. So it's a lot cleaner when we are in trig form. Alright, last thing. So kind of remembering our identities and also thinking about de Moivre's theorem, I want you to find cosine of theta plus I sine of theta squared. And I want you to do that using de Moivre's theorem and also just using algebra and multiplying these out. Okay, so we basically did this in yesterday's notes as well, but it's good practice, and I just want to make sure we see this comparison again or understand using our trig identities and how this relates to some of the other things that we're seeing now, in particular here, de Moivre's theorem. So cosine of theta plus I sine theta squared, using de Moivre's theorem, I square the r value and I multiply theta by 2. So I get 1 squared times cosine 2 theta plus I sine 2 theta. Just multiplying this out, if I write these as two separate binomials, I multiply them out, I get cosine squared theta plus 2i sine theta cosine theta plus I squared sine squared theta. Now, simplifying and combining like terms, I squared is negative 1, so I can bring this to the front with the real terms. So I end up with cosine squared theta minus sine squared theta. And then I just rewrote the 2 in the I 2 sine theta cosine theta. So 2 sine theta cosine theta is sine of 2 theta from my double angle identities, and cosine squared theta minus sine squared theta is cosine 2 theta from my double angle identities. So again, it was just more for practice to see how de Moivre's theorem works, or one way in which it works in this case, and it's from our trig identities. Alright, so we want to understand complex conjugates, the trigonometric form of complex conjugates, and operations with complex conjugates. Recognize that trig identities can be useful in simplifying complex numbers. They can also be useful when buying puppies and training apes.